Hello everyone. In the previous video, I gave a brief rundown of the motivations behind quantum computing and some of the things it is capable of accomplishing. In this video, we will start with the most fundamental mathematical basis for quantum computing by establishing a formalism for quantum bits or qubits in both the context of single and multi-qubit systems. While a classical bit has its state represented by either a 0 or 1, we describe the state of a qubit as a complex two-dimensional vector with unit norm, where one dimension corresponds to the 0 state and the other to the 1 state. For instance, if a qubit is in the state 0, we can represent this with the vector 1, 0. On the other hand, if the qubit is in the state 1, we instead represent it with the vector 0, 1. That being said, the state of a qubit is not restricted to only these two vectors, as that would be no different from just a classical bit. Instead, this qubit can be in superposition between states 0 and 1, just as how a quantum mechanical system can be in a superposition of different energy eigenstates. We denote this general superposition as a vector of the form alpha, beta, where the absolute value of alpha squared plus the absolute value of beta squared is equal to 1. While I have been using the typical vector notation that you would usually see in linear algebra thus far, it should be noted that in quantum computing and in quantum mechanics more broadly, we usually use a different notation system known as Bra-Ket Notation. Since I will use this notation going forward, it will be useful to explain how to translate over familiar linear algebra concepts into this formalism. In Bra-Ket notation, we have three fundamental objects: kets, bras, and operators. A ket is denoted as follows and simply refers to a column vector. For our purposes, we denote the states 0 and 1 as being equivalent to the following column vectors. Using the standard basis, we can define any general vector in C2 as a linear combination of these kets. A bra is denoted as follows and is simply the conjugate transpose of the corresponding ket. This means that we simply transform the column vector represented by the original ket, conjugate all its elements, and then transform it into a row vector. We can combine bras and kets like this, omitting the duplicate line in the middle to denote an inner product between the two vectors. The last major type of object we deal with in this formalism are operators. These can simply be thought of as just matrices in the finite dimensional setting, which is what we will be using for this course. You can act with these operators on kets or bras just as you would matrices with column or row vectors. As an exercise, try to write the following states in terms of the Bra-Ket formalism as described, using the 0-1 basis we described previously. Afterwards, compute the inner product of the two states in Bra-Ket form. Finally, I want you to apply the z operator to the plus state and write the result in terms of the plus-minus basis. Pause the video and try these problems. Okay, so writing out the plus and minus states in terms of the standard basis expansions, we have the following. If we take the inner product of these two states, we can write out the results as follows. Here, we have that the inner product of any vector with itself is simply its norm squared, which is just 1 since all these vectors have unit norm. Furthermore, since our basis vectors are orthogonal, the cross terms vanish, giving us a final result of 0, meaning that the plus and minus vectors are orthogonal. Lastly, if we apply the z operator to the plus state, we get the following state in the standard basis, which is simply the minus state. I won't talk too much about operators in this video, but in the next video, when I discuss quantum gates and circuits, I will go into much more detail about how we actually perform computation with qubits. While qubits can take on any state in C2 with norm 1, it should be noted that if we try to measure the qubit, we can only observe its state as being in one of two orthonormal vectors. For one, if we are measuring with respect to the standard basis, and we measure some state, let's say alpha 0 plus beta 1, where alpha and beta are non-zero, we will only get either 0 or 1, and the state of the qubit will collapse accordingly to either 0 or 1, depending on what we measure, destroying the superposition. Mathematically, this is equivalent to projecting the state vector onto one of these standard basis vectors with a given probability. The probability of measuring 0 or 1 is directly dependent on the coefficients alpha and beta, with the probability of measuring 0 being the absolute value of alpha squared, and the probability of measuring 1 being the absolute value of beta squared. It should be noted that the choice of basis here is somewhat arbitrary for qubit states. For instance, while we will typically use the standard basis, there may be instances where it is more convenient to use the plus-minus basis defined previously, in which case we will define the state accordingly. Similarly, even though we usually measure with respect to the standard basis, it is also possible to measure with respect to a different orthonormal basis, such as the plus-minus basis. Consequently, it will be useful to remember these plus-minus states for future references, as they will come in handy quite often. One important fact that I should also mention before going on is the difference between global phase and local phase. In particular, adding a global phase to any quantum state in general, meaning that we just multiply the entire state vector by some complex number with unit absolute value, does not change the state. Hence, there's actually some redundancy in our state description, as the states psi, minus psi, and I psi, for instance, are all the same. However, local phase, meaning phase differences between linear combination coefficients, should not be ignored. For instance, going back to the plus-minus states described previously, in the standard basis, both states seem pretty similar since they both result in either 0 or 1 with probability 1/2 when measured. However, these states are orthogonal to each other and are therefore entirely distinct. Okay, so I've talked a lot about single qubit systems, but there's really very little we can do with only one qubit. So let's talk about multiple qubits. Before we get to n-qubit systems, let's first think about how we might represent two qubits. Classically, we have that two qubits can take on four different values: 0, 0, 0, 1, 1, 0, and 1, 1. Drawing analogy from the single qubit system case, this means that we want to use a four-dimensional complex vector space to represent the state of two qubits, where each standard basis vector corresponds to either 0, 0, 0, 1, 1, 0, or 1, 1. One natural question is how these states relate to these single qubit states. Well, we have that each basis state for two qubits is simply the tensor product of the two basis states that compose it. The tensor product, denoted using this O times operation, combines two matrices as follows. Suppose we have a matrix A, defined as follows, and a matrix B. We then have that A tensor B is given by this block matrix, where each block consists of B scaled by an element of the A matrix. Consequently, if A is a m by n matrix and B is a p by q matrix, the resulting output is of size mp by nq. The tensor product has some nice properties, some of which I have listed here. Note that this operation is not commutative, meaning that in general, A tensor B is usually not equal to B tensor A. Getting back to the two qubit standard basis states, we therefore have the following definitions. Okay, but now suppose we have one qubit in state psi and another independent qubit in state phi. How do we represent the joint state of the system? Well, we can simply take the tensor product of the two states, giving us the following state. States for two qubit systems that can be written as a tensor product of two single qubit states are known as separable or product states. Not every two qubit state is a product state. For instance, consider the equal superposition of 0, 0 and 1, 1. No matter how you look at this state, there is no way to factor it into a product of two states. If a state cannot be written as a single tensor product, it is known as an entangled state. To understand what this means intuitively, we need to extend the notion of measurement to multiple qubits. Just as in the single qubit case, we can measure all the qubits with respect to the standard basis to get a finite set of outcomes. In particular, if we measure two qubits, we can get one of four basis states, where the probability of getting each is simply the absolute value of its coefficient squared in the basis expansion of the two qubit state. However, what's more interesting is what happens when we measure only one qubit. This is known as a partial measurement. Mathematically, this means that rather than projecting our vector onto one of four basis vectors, we are instead projecting it onto one of two 2D subspaces. For two qubits, this gives us two different measurement outcomes that each occur with the following probability. This notion of partial measurement can give us some intuition behind entanglement. In particular, entangled qubits have measurement outcomes that are dependent on each other and cannot be separated without destroying the original state. For instance, compare phi plus to the state 0, 0 plus 0, 1. In the case of the latter, if we measure one of the qubits, we have that the other qubit will remain in the same state, meaning that these qubits are independent of each other. However, in the case of phi plus, we have that if one qubit is in state 1, we automatically know that the other is in state 1 as well, and similarly if one qubit is in state 0. Consequently, since these outcomes are correlated, this state is entangled. This state that I mentioned is usually discussed in tandem with 3 other maximally entangled states. Collectively, these 4 states are referred to as the Bell basis, and are useful since they describe a basis for 2 qubit states, where each basis vector is a maximally entangled state. We can easily generalize the formalism for 2 qubit states to n qubits, where there are now 2 to the n standard basis states given as n-wise tensor products of single qubit basis states. The definitions of product states and entangled states generalize accordingly to these systems as well. We denote the vector space for n-qubit systems as C2O times n. Furthermore, just as before, we can either measure all n qubits or we can perform partial measurements of subsets of qubits, and we'll see many uses of this later on. Altogether, we developed a mathematically rigorous framework for working with single and multi-qubit systems in terms of complex vector spaces and tensor products. Nevertheless, it remains to be seen how we can actually perform computation with these states. We will explore this in the next video, where we discuss quantum gates and circuits. I hope you enjoyed this video, and I will see you next time.